Now notice in this one that we have a function minus a function inside, but the whole thing is getting squared. So if we are thinking about the sum and difference rule, which says if you started off with two functions adding or subtracting them, well, we can't quite say that that's what we have here, because I have a function subtract another function, but then the whole thing is squared. And this formula doesn't have anything for that red where I'd have the whole thing squared. But if I could rearrange this one, so that it looked like a whole bunch of functions adding and subtracting, then I could just do the derivative of each one separately. This isn't so bad. I have squared here. What does squaring mean? Multiply by itself. So if I think of multiplying it by itself, that actually wouldn't be too hard to do. Multiply everything through. And you would get x to the 4 minus 8x squared plus 16. And now we've got a bunch of individual functions that we know how to take the derivative of. And we can find the derivative. So I'd like you to try part B. Come around and help you if you get stuck. A lot of you had the right idea. Cube root you can change to x to the 1/3. Then once you distribute this, now x squared is like 6 over 3. So if I multiply things with the same base, I add the exponents, you're going to get x to the 7 over 3 plus 3 x to the 4 over 3. Now when I bring the 7 over 3 out in front, that will give me 14. You can either think of it as 42 divided by 3, or maybe you divide by 3 first. That's technically what I do more often. Work with smaller numbers. So I divide 6 by 3 to get 2, and then I still have to multiply by 7 to get 14. Subtract 1 from the exponent. Again, here we'd have just 4. Subtract 1 from the exponent. All right, try part C if you haven't started already. I'll show you a couple of the methods that I saw coming around. I like the creativeness that you guys were showing. Okay, one way to look at this is to unadd fractions. Right? When you add fractions, you need a common denominator, and then you add the tops, and then write it all over the common denominator. To sort of unadd fractions would say, well, right before this step, I might have had this. Already common denominator. The next step would be to combine it. Now, they don't teach a lot of unadding fractions in high school, because most of the time they're just worried about you adding fractions, and that's hard enough as it is. So here, though, by unadding them, well, in the first expression, I could actually simplify this to get 2x to the 6 over 3. And the second one could simplify to be 3 over x. Now I'm going to just take the time to write all of my ugly looking 6. All of my x's with in the numerators with exponents, so then we can apply our rules and we can find our derivative. Bring the 6 out in front, subtract 1 from the exponent. bring the negative 1 out in front, and subtract 1 from the exponent. And then we have our derivatives. So this is kind of the idea of unadding fractions. You can split up something, and then that would, in simplifying it. I saw a number of you using factoring, right? The bottom was a problem for you, so you factored it out. And then you distributed that 1 over 3x to each one separately, which is basically the same idea. Okay? Some of you, when you rewrote it, put the x to the negative 1 already in the top. Now, if you move the x to the top of the fraction, the 3 doesn't move. So that's one thing I liked looking at something like that. You get so tempted, you think that 3 and that x are such good friends, that the 3 would have to move with the x. But it's just the x and the exponent that would get moved to the top of the fraction. So if you took either of these and then distributed next, you will get the exact same thing that we got on the left in the green, and the derivative would be the same that way as well. So a lot of calculus and a lot of university math is you have these algebra skills. Sometimes you have to be creative with them and think, what can I do to manipulate this equation to get it into a form that I can work with? And the way this was originally, we couldn't take the derivative of that. But if we broke it up into different parts, into a form that we could do the derivative of each thing separate, then we could find it.